The ball is bouncing, but as I mentioned in my previous video, it's bouncing at the same angle regardless of where it hits on the vertical section of the paddle. We'll start with a demonstration to illustrate the problem. Here we can see that the normal is the same across all of the vertical surface, and when the ball hits that surface, it bounces the same. Now I'm going to adjust the normal based on how far away the ball is from the center of the paddle. We can see that by adjusting that normal, the ball bounces at a sharper angle. We're not changing the bounce code, only which normal it should use. We're going to get this working using a technique called red-green refactor. When we're in the red, it means our problem is not solved, meaning our ball is not bouncing using that normal technique. When it's green, the problem is solved, but it may be a little messy. After the refactor stage, the problem is solved, and it's solved in an elegant way. So right now we're at the red stage, so let's just get it working however we can. So we're going to go back into the ball collision code. Previously, we would get the normal from the collision. Instead, let's take our collision normal and rotate it based on how far away it is from the center. So we're going to start by checking if we actually collided with a paddle and not the wall. We can do this by first going back into our paddle class and giving it a name so we can identify it. So let's go over here and give this class name paddle. And then we can go back into the ball script and start adjusting our normal. So let's go ahead and make normal a variable here. We'll make it equal to collision.getNormal. So what we want to do is rotate this if we collided with a paddle. So we can check that by saying if collision.getCollider is a paddle. And if it is, then we can start adjusting our normal. I'm going to cache off the paddle by saying collision.getCollider as paddle, so we can access its variables very easily. And for clarity, I'm going to make impact a variable here equal to collision.getPosition. And then before we can continue, I need to know how large the paddle is. I'm going to hit controller command click to jump to our paddle class like that. And I'm just going to add a function here called getSize. GetSize should return a vector 2. And I want to be able to return the value of our collision shape right here. So to do that, I'm going to controller command click the collision shape and drag it into our script. Now we have a reference to it. I'm just going to rename this to collision. And now what I can do is I can return collision dot shape dot get rect, so the rectangle of this collision, and I just want the size of it. I'm going to save that and go back to our ball script. Now we have our size. So I'm going to store a reference to our half height. So the half height of a rectangle would be the paddle's size, the y component, over 2. So we can imagine that in our paddle, we start here, we go up half height to get here, or we go down half height to get here. So back in the script, I'm going to go to ball, and I am going to set up something where in our paddle, I want to get a value where it's equal to 0 up here, and it's equal to 1 all the way down here. So 0, increasing to 0.5, increasing to 1. I can use something called inverse lerp to do that. Inverse lerp is similar to, if you remember from our previous video, in the shaders, we were discussing how we could use the mix function to mix between two values. This is like the inverse of that. So what it's going to do is going to take a value say two values, so like the ends. So it could be some start to some end, and given some value, it will return like the percentage of the value between start and end, which is what we need here. So what we could do is replace the start with our paddle dot position minus the half height, which gets us up here. And then we could go from the paddle dot position plus half height. That gets us to the bottom. And that's our start and that's our end. And then we want to get the percentage of a value in here, which is just going to be our impact's y position. And now we have that value from 0 to 1. So since we have that value, we can use that to get the angle that we should be at. And more precisely, I want to get the angle that I should rotate the normal by. So first of all, let's call this our normalized impact. And then let's make a variable called angle, and this is what we're going to rotate our normal by. We're going to use the lerp here. Lerp is, it's the same thing as mix, essentially, back on our shaders. And so we're going to lerp from some starting rotation up to some ending rotation. I found that pi over 8 is good. So I'm going to go from pi over 8 up to, all the way up to pi over 8 as our rotation. And I'm going to use that normalized impact to do that. And then finally, our normal is just going to be our normal dot rotated by that angle, only if we've collided with the paddle. If we haven't collided with the paddle, then the normal is the same as it was before, and then we bounce using it. And just make sure, instead of using that, we pass in our normal here. Let's see what happens. Okay, it's a little issue. Let me make sure we're using just the y here. And we're using the actual y coordinate here. So looks a little bit, yeah, that's good. We're getting some sharper angles. We'll fix that part in a minute too. On the right side though, this shouldn't actually be correct yet. The reason is that on the right side, the normal's facing this way. So we want to actually flip our rotation there. So we can just take our angle and multiply it by the sine of our x-coordinate. This isn't the sine like trig, this is just the positive or negative value. So if it's positive, we don't change anything, but if it's going the other way, we'll flip our angle to correct our rotations. We're getting close, but we could see what was happening on the tops of the paddle there, where it kind of got stuck a little bit. It didn't really bounce how we wanted it to. So we're going to figure out how do we address that. To do that, we're going to use the dot product. We know that if the normal is pretty close to being vertical, we don't want to rotate it. So we're going to take our normal vector and dot it with the up vector. And if they're reasonably different, we can go ahead with our rotation. But if they're pretty close, the normal to the up vector, we're going to leave it as is. What we're going to do is we're going to say if the normal dotted with the up vector, should be 0, -1. We're going to say if that value is less than 0.7, then we can go ahead with this logic, which means that the normal is fairly different from being the up vector. If we were to increase this value, then that would mean the normal would have to be very, very close to being that up vector. But because we can bounce on these corners, it isn't necessarily going to always be just the up vector. So that's what this 0.7 is doing. It's giving us this tolerance. We could also make it like a variable if we wanted to. So you allow designers to change that, but I'll leave it as 0.7 for now. And this would work on the top, because the top normal vector is going up. But it wouldn't work on the bottom because that would have the normal vector of 0, comma, positive 1. So to handle that case too, all you have to do is also take the absolute value of this, like so. So it's pretty tough to see that this works when the ball's going so fast. So just to make it clear, I'm gonna temporarily slow the ball down. Drag these values down to 200 to make it easier to test. So we can see it slowing down. If I bounce here, it bounces normally. This is what we wanted. So there's still some issues here. Based on how the ball is launched, it can be deflected at these very steep angles, and it actually takes way too long to get across the entire court. So let's go ahead and resolve that. Coming back to our reflection demonstration, we can see that if we imagine that we have a positive coordinate space here, that what we'd want to do is say if this angle is too large, we just want to constrain it by some threshold. I'm going to make a function called clamp vector by angle, and this is going to take in a vector v and an angle type float, and going to return a vector 2. What this is going to do is, first, for now, we're going to assume a positive coordinate space. So in that positive coordinate space, we could just check if the vector's angle is larger than our angle threshold. Then we need to correct it. And we could correct it by making a new variable called constrained vector. And we'll set it equal to a new vector. First, we just want to get the normalized version. So we'll take the cosine of the angle and the sine of the angle. And we want the length to be the same as it was before. So we'll just scale it by the original vector's length. Like so. And then if that's the case, we can just return our constrained vector. If the angle was okay, then there's nothing to change. We can just return our vector back. Oh, and this is vector 2, not 2D. So this works in a positive space, but of course the directions could be negative or in any quadrant of the coordinate space. We need to handle those cases. So what we can actually do is, let's make a new variable called absolute vector. I'm going to assign it to v.absolute, and this is just going to take the absolute value of all of the coordinates in the vector. And rather than using v, I'm going to use this absolute vector. And now this absolute vector, if its angle is outside the threshold, we want to do the same thing as we were doing before. However, now we only have the positive version, so we just need to fix that. So we can actually check if our vector.x was originally negative, then we'll take our constrained vector and make that negative 2. And similarly, if our y was originally negative, take our constrained vector and make it negative 2. And then after that, we're done. Now we just need to use this function. So in our physics process, we were bouncing the ball across this normal to get our velocity. What I'm also going to do now is, after we bounce, we'll make sure that, so I'll use our clamp function. I'm going to clamp the velocity by, let's just say, pi over 4. Let's see what happens. So if we're at these sharp angles, nice. It's not, we still get this fun factor because it can still change how we play, but it's not to an extreme where it takes so long to get across the court. So now what we have works, but the collision method is getting a little bit too large and a little bit messy. We generally don't want to be just checking, oh, did I hit the paddle? Did I hit this other thing? Did I hit this other thing? Because then this function is going to get very large and unwieldy pretty quickly. So let's move on to the refactor stage. Godot does not have interfaces, but we can check if a method exists before calling it. So I want to move our collision logic. I want to delegate that to what we collided with. In this case, that is the paddle. So what I'm going to do is, rather than checking if it's a paddle, let's check if the collision dot get collider. I want to check if you have a method. I want to check if you have a method called handle ball collision. And if you do, we can go ahead and modify the normal, however the collided object wants to. So what I'm going to do is set the normal equal to collision dot get collider dot handle ball collision. And what this is going to do is I'm going to take in a impact position, which would be the collision dot get position. I'm going to take in the normal, and I'm going to take in the ball's velocity. We'll be using that a little bit later, but we'll pass it in now. And so what I'm saying is if I collide with this thing that has this method, I'll let it modify the normal for us. So right now this wouldn't do anything. We want to actually move this logic. Into the paddle. So I'm going to cut that, and I'm going to go back to paddle. I'm going to make a function called handle ball collision. I'm going to take impact position, a normal, and a velocity. And I'm going to return a vector 2. After that, I'm going to paste what I had in from the other file. Fix the spacing, tab over here. And there's just a few variables we have to rename. It's not collision anymore. It's now just impact. Well, actually, we already have the impact variable, so we can just get rid of that. And not all code paths return a value. Yes, so we have to say if in the event that we did collide with the top of the paddle, if we did collide with the top of the paddle, then we'll just return the regular normal back. Like so. And still not all code paths are returning a value. Let's just go ahead and return this instead, like so. And one other thing, we don't need paddle anymore because we are the paddle now. And we don't need paddle dot get size anymore. Just do get size. And we're just using our position now. And we're using our position still. And now this is all contained in here. If I save this, I'm going to go back to the ball. We don't need this anymore. And we don't need this. We can tighten up our spacing like so. And now we're just saying, look, if I collide with something that can handle this, I'll allow that object to handle it, rather than polluting our physics process function with a whole bunch of cases that we'll have in the future. Let's go ahead and try this out. It should be the same as before. Nice, that looks good. Let's also go back into the ball and put our speeds back to normal here. It's at 700 and 400. Try again. All right, now we have like a game that could be fun now. And we have some interesting angles that we're getting, which is pretty cool. Thank you for watching. Next time we'll set up the AI paddle controller.